Hey students, how you doing today? This lesson is not required. This is I wouldn't even call this an advanced lesson. This is just it's almost like a story. Because when I was in high school, I took Algebra 2, and I don't remember ever learning about horizontal dilations at all. Then I went to college, and when I was in college, we never talked about horizontal dilations at all. I know I didn't talk about them in college. I don't remember talking about them in high school. So I guess it's possible we did learn them in high school. I just don't remember them. But either way, I'm not sure horizontal dilations are always 100% necessary. And that's in the title of this quickie lesson today. Are horizontal dilations necessary? So let's look at this equation right here. Suppose I had y equals 2 times the absolute value x plus 5 over 3 minus 4. We're specifically looking at this inside stuff. So this one has a vertical dilation by a factor of 2 and a horizontal dilation by a factor of 3. I'm just going to quickly write that. So vertical dilation by a factor of 2, horizontal dilation by a factor of 3. But absolute value x plus 5 over 3. Now if you have a fraction inside an absolute value, you could break it up into the absolute value of the numerator and the absolute value of the denominator. And what's the absolute value of 3? It's 3. So this becomes absolute value x plus 5 over 3, which is simply equal to 1/3 absolute value x plus 5. And then if I took that 1/3, so if this became that, and then I took that 1/3 and I multiplied it by 2, I would get 2/3 absolute value x plus 5 minus 4. And this equation only has a vertical dilation. But it's by a factor of 2/3, which is kind of awkward. So this is kind of interesting, I thought. So I actually put these two graphs on Desmos. Let's take a look at this. Make it screen a little bit bigger. All right. So so over here, I graphed that first equation I told you about. And let's see if I get rid of that one, and get rid of that, and get rid of that. Okay. So the only thing that's up here right now is this graph, is this red graph. But now, if I go, and this point right here at the bottom is -5, -4, and because of the horizontal dilation by a factor of 3, I could go over 3 units. A vertical dilation by a factor of 2, I go up 2 units, and I end up at this point of -2, 2. But then, if I graph, so then the second equation I came up with that just had the vertical dilation, that was this one, and when I click on this button, boom, it's the exact same graph. Check it out. It is the exact same graph. But then, what would be weird would be then the next key point, because if this one has a vertical dilation of 2/3, so if you went to the right 1, you'd go up a value of 2/3, which would then give you a key point of -10/3 for the y value, which is on the line. So, answer the question, are horizontal dilations needed? Well, if you want your graph to be pretty happy points, like when I used this, when I used this, the one with the vertical of 2 and the horizontal of 3, this had a nice clean coordinate for this point. Whereas this point, this would be for the vertical dilation of just 2/3. It's not as clean of a point. So if you need clean coordinates, you might want to use the horizontal of 3 and the vertical of 2. Whereas if you just want an accurate graph and you don't really, as long as the coordinates are correct, it's accurate, you could just do that. So in an absolute value graph, a vertical dilation of 2 and a horizontal dilation of 3 is basically mathematically equivalent to there being a vertical dilation by a factor of 2/3. Interesting. Now, if we looked at the same thing but using a quadratic. Hello, good sir.
Hello.
What's going on?
She wants me to deliver the thing in the folder to you.
Oh, okay. Will you just leave it on that desk?
Okay. Which one?
Right, that one right there.
This one?
Yeah.
Okay.
Awesome. Thank you.
Yeah.
All right. So if this was my equation right here, same type idea. This x plus 5 squared, x plus 5 over 3 squared can become x plus 5 quantity squared over 3 squared, which becomes x plus 5 squared over 9, which would become 1/9 x plus 5 quantity squared. And if I took this and I set it equal to this and I multiplied it by this 2, I'd get 2/9 parentheses x plus 5 quantity squared minus 4. Now, I don't have a Desmos checked for this one, but my point is that if you have a vertical dilation by a factor of 2, a horizontal dilation by a factor of 3, that is equivalent, in a quadratic at least, and this is only talking about quadratics, this is not talking about absolute values, that this is equivalent to a vertical dilation by a factor of 2/9. So in the absolute value function it was one way, whereas in this other one it was slightly different with this vertical dilation. So you never have to use horizontal dilations. You can, with almost every parent function we're going to be dealing with, you can almost always find a mathematical way to pull that horizontal dilation out and combine it with the vertical dilation, which means you never have to do horizontal dilations if you don't want to, which I do think would make a lot of these problems a little bit easier for people, because horizontal dilations really confuse people, at least compared to vertical dilations. So that's some food for thought for you. And is this stuff that you can use on your test next Tuesday? Definitely. And I recommend it. Have yourself a great Wednesday evening. And if today's quiz didn't go well, just remember, it's accuracy, but you also can't spend the entire, all the world and time in the world working on these problems. You do need to be a little bit timely about it. So practice working the problems quickly, efficiently, and accurately. Have a great night, and I'll talk to you tomorrow, everybody. Bye-bye.